I'd like to start this video by just introducing you to a couple of circuit symbols and their interconnections. Just a few important ones. By no means is this inclusive, it's just touching the surface, but I think it's worthwhile. Here's a battery and how we basically construct the schematic symbols representation for a battery source. We have the source itself here in the shaded region that encompasses the whole thing. There's an internal resistance. That's a resistor. It's a symbol for a resistor. And then we have the EMF source here. And the EMF source has a long side, which is positive, and a short side, which is negative. All right, so there it is again. I'm going to put that ultimately in a circuit here. Source of EMF, the long side is highest potential. Short side is lower potential. Now, how do we include an ammeter? Ammeter is a current meter. The current in the circuit has to flow through the meter without disturbing the function of the circuit. That's crucial for the basic ammeter and voltmeter. They have to be included in the circuit to measure the quantity without disturbing the circuit. So an ammeter, since it's measuring current, has to be in series with the circuit. And it has to look like essentially a zero resistance element. Otherwise, it's going to affect the circuit. Okay, so we're going to hook it up in series through another resistor here. And there we have a little circuit, complete path. So low internal resistance on the ammeter, always in series. And on the flip side, we have the voltmeter. So here it comes. And we always hook a voltmeter across, not through, because it's measuring potential difference. Now again, when you hook the voltmeter up, you don't want to disturb the circuit, but you want to measure the voltage difference, the potential difference across a circuit element, or several, two different places in the circuit. So it's got high internal resistance, ideally infinity. It's always connected in parallel because you don't, you're not running current through it. You're measuring potential difference, not current flow. And you don't want this to be an actual path for current to flow. Generally speaking, there'll be a tiny microamp or nanoamp or picoamp amp trickle in order to actually take the measurement, but as low as possible. A couple other things we have here. I just threw in another resistor with a line through it, which means it's a variable resistor. And when it's hooked just in a line like this, where you're just varying the resistance of this element, it's typically called a rheostat. And I've got a arrow connecting up to this resistor. So this whole thing here with 3 points, 1, 2, 3. If we run a current through here, there's a voltage across here. Well, from here to over here in this pointer, typically like a slider on the device itself, you get a varying potential across here, or from the middle to the other end. So this is called a potentiometer. It varies the potential from one side to the middle. So there's a few circuit elements and their schematic representations. Let's now consider the work and power in a circuit element and in a source as well, identifying the various aspects of where the work, where the electrical energy, how it's being partitioned. All right, so here's a circuit element. And we have current going in. Between A and B, we have a potential difference. We have VA and VB. Now, the differential work that's done by the electrical energy transitions, I'll just say, is volts times charge, but differential. So to move a charge across points A and B, it's that potential difference times the differential charge. So V dq. So dq is I dt. So the amount of charge is rate at which charge flows times differential time. So we transpose the differential into dt. Well, power is rate at which work is done. So then just divide by dt and you get VABI. So we now have defined power as volts times current. Potential difference times the current flowing. For a pure resistance, very common in electronic applications. Power is volts across AB times I. Simple as that. But we can write it in different ways because V is I times R, so this becomes I squared R. And then current I is V over R, so we can write this as V squared over R. Now consider the power output of a source. Don't have a picture right here, but we've analyzed that already. So we have a source, a battery, say, and its power output is terminal voltage, VAB. So we could look at this, voltage across here. If this was a battery, which it's not, but we'll pretend it is, times the current gives the power delivered to the circuit. But that's not the whole story. The voltage, VAB, is the EMF of the battery minus what's dropped across the internal resistance. We discussed that. So that's what VAB is. We're going to break this apart a little bit. So this is EMF times I minus I squared R. What are these various things? VABI is power dissipated by the external circuit, or a resistor, say. EMF times I. Well, if you look at the internal of the source, the EMF is what it produces, times current passing across, is the total power that the source delivers. So power supplied to circuit by source. But when I say circuit, I mean the whole thing, including itself. Speaking of itself, there's that internal resistance. And this resistance times I squared is a power term. That is the power dissipated by its internal resistance. So that's power dissipated in the source. This is what causes the battery to heat up. If you ever feel your laptop on your lap, with the battery pretty close to your leg, you might feel it getting really warm. Part of that is because of this I squared R. Now the power input to a source. So that's considering when you're charging the battery, say. So power, VABI. But this time, the terminal voltage, VAB, times the current, is the EMF, the source, but you're driving current the other way. So the IR, the internal resistance, times current increases the voltage manifested across the battery terminals. All right, so that's the charging consideration. So we can say EMF times I plus I squared R. EMF times I, that's the power, you could say, against the non-electrostatic E field. This is what charges the battery. So that power is converted into chemical, potential energy. So that's not causing heat. That's recharging the battery. Then you have this I squared R. So the laptop on your lap, if it's plugged in, so I'm talking about the discharge dissipating heat, but also charging dissipates heat just as well. So this I squared R is power dissipated in the source again as a result of current going the other way. So that's a breakdown of the various aspects of power in a circuit element and in the source.